Welcome back, everyone. Today we're going to talk about a variety of higher order differential equation called a homogeneous ordinary differential equation. Now, some of you with a very good memory may be thinking back to some of the very first videos that we recorded and saying to yourself, didn't we already cover homogeneous differential equations? Wasn't that a specific variety of differential equation in differential form? And that's true, but one of the unfortunate aspects of mathematical terminology is that a few adjectives tend to get overused, and you tend to see the same word used to refer to a couple of different things. And so when we say homogeneous ODE, talking about a higher order differential equation, that's going to be different from the ODEs that we studied back in video 4 or 5 or whatever, which were homogeneous of degree alpha. So I'm sorry, I didn't make the rules, I didn't make up the language. It's going to be the same word, but it's going to have a different meaning. The way that I've sort of organized the next couple of sections is, when we get to the most complicated versions of this kind of question, the most complicated versions of this question are going to have to be solved in maybe a 3, 4, 5 step process. So the way that I've organized the videos is, I'm going to start by introducing ODEs that are simple enough that all we have to do is step number 5. And in the next video, I'm going to make the ODEs more complicated, and they're going to require us to do steps number 4 and 5. And then the ODEs are going to get even more complicated, and they're going to need us to do steps 3, 4, and 5. And finally, the most complicated will require us to do all 5 steps. So what does a homogeneous ODE mean in this section? An nth order ODE is called homogeneous if it has the form some function of x alone, let's call it alpha sub n of x, multiplied by the nth derivative of your output variable y. Then take another function of x alone and multiply it by the n minus 1 derivative, and so on and so forth until you get to a function of x alone times the first derivative, a function of x alone times the original function, the 0th derivative. And here's the important thing for a homogeneous ODE, that expression has to equal 0. So this is not the same as homogeneous of degree alpha that we saw in video whatever when we were talking about differential equations, first order in differential form. This is a different definition. Now in the real-world applications that we looked at yesterday, we had 2 examples of homogeneous ODEs. The ODE corresponding to the spring mass system, mass times x double prime. The second derivative I'll specify of x with respect to time, plus a constant times x equals 0. This was homogeneous with the output variable called x and the input variable called t. The right-hand side of the equation was equal to 0. We had a function of the input variable alone, the constant function m. The function multiplied by x single prime is just 0 in this case. That's why there is no x single prime visible. And the function multiplied by the 0th derivative, x with no prime, is the constant function k. And then we have 0 on the right side. So this would be a homogeneous second order differential equation. The differential equation corresponding to the RLC circuit is also second order homogeneous. The function of the input variable time corresponding to the second derivative is the constant function L, representing the inductance. The constant function, the function of t alone, multiplied by the first derivative, is the constant function representing the resistance. And the function of the input variable alone, multiplied by the 0th derivative, is 1 over the capacitance, and then we have that all-important 0 on the right side. For some non-examples, for some ODEs which were not homogeneous, we had the other two ODEs that we saw yesterday. The one corresponding to the deflection of a beam, for example, is not homogeneous because we have a function of x which is not multiplied by any y's. Here, all the functions of x are multiplied by y. There are 0 functions of x that are not attached to any y's. So this is not homogeneous because of the function w of x representing the load. Additionally, the differential equation that we gave for the pendulum is non-homogeneous. For the pendulum, we had that the second derivative of theta with respect to time plus a constant, let me just call it k for short, sine of theta was equal to 0. In this case, we do have the 0 that we need on the right-hand side, but the problem in this case is that the output variable theta is inside another function sine. In our definition of a homogeneous ODE, y, y prime, y double prime, etc. are all outside of functions. It's sort of like a polynomial in many ways. This is sort of the equivalent of a polynomial for differential equations. The coefficients are replaced by functions of the input variable, and the x's are replaced by different derivatives of the output y. Now, here is why homogeneous ODEs are so special. Homogeneous ODEs are unique because if you have two individual solutions to a homogeneous ODE, then any linear combination of those two solutions is a brand new, also perfectly valid third solution. In case you're not familiar with the language linear combination, let me state that in a principle, in a theorem, which is loftily named the superposition principle. Suppose that you have two solutions to a homogeneous ODE. Let's just call them f1 and f2. If those two functions, y equals f1 and y equals f2, are solutions, and you take a number c1, any number, and multiply it by the first function, any number multiplied by the second function, add them together, this is also a solution to the ODE, regardless of what values you choose for C1 and C2, for all C1, C2 real numbers. So superposition principle says that if you have two solutions, you can combine them to get a third and a fourth and a fifth and so on. You can actually get infinitely many new solutions by choosing different values for C1 and C2. But when we're solving a differential equation, we're not just trying to find a bunch of solutions, we're trying to find all possible solutions. The question is, when do you know when you have all the solutions to a differential equation? When do you know that you have all of them as opposed to just some solutions? In answer to that question, we're going to introduce a new theorem which requires a new piece of terminology called linear independence. If you've taken linear algebra, you're probably already familiar with the concept of linear independence of vectors. And linear independence of functions is a very similar concept. Definition. So we've got a collection of functions, let's just generically call them f1, f2, fn. The functions in this collection are said to be linearly independent if the only way to make C1 times F1 plus C2 times F2 plus C3, F3, and so on and so forth up to Cn the only way to combine those functions and get 0 as a result is to sort of do it in a really trivial way, is to make all the constants C1, C2, Cn, etc. equal to 0 themselves. There's no sort of non-trivial, meaningful way to combine the functions f1 through fn and get 0 as the result. Let me give you an example of a collection of functions which is linearly dependent, by which I mean that the functions in this collection are not linearly independent. We have cos squared, sine squared, tan squared, and secant squared. Now let me suppose that I was going to try and take these four functions, and by multiplying these functions by constants C1, C2, C3, C4, I want to try and construct the function 0. And I'm going to see if I can do this in the way that's not like completely trivial and silly, which would be to just set all the constants equal to 0. I want to see if there's a non-silly, more meaningful way to actually make this happen. Now at first it may not seem like this is possible, but we have to go back and think about trigonometry, which gave us some relationships between the function cos squared, sine squared, and a relationship between the functions tangent squared and secant squared. So in particular, there was a relationship that said that if you take sine squared, that's the same thing as 1 minus cos squared. And there was another sort of version of the Pythagorean identity, which said that if you take secant squared, then that's the same thing as 1 plus tangent squared. So using those identities, let's go ahead and rearrange this a little bit. Let's combine some like terms. We have C1 minus C2, that's the coefficient on cosine squared now. That's what we get if we combine this term with this one. We also have C2 tan plus C4 tan squared, C3 plus C4. And then we have some constants. Then we have C2, C2 times 1, and C4 times 1. That needs to be equal to 0. Can I make this happen in a way that's not completely trivial and silly, where all the constants are just equal to 0? Now, I think in this case, probably the best way to actually find these values of C1, C2, C3, and C4 without using linear algebra is just to do some guessing and checking. Like, for example, if I want to kill this cos squared term, I can make a C1 to be the same thing as C2. So maybe I'll try C1 equals C2 equals 1. Now, as soon as C1 equals C2 equals 1, then this C2 term also must become 1. So that's going to force C4 to be negative 1 to cancel with this positive 1, which C2 is now equal to. Now, if I want to annihilate the tangent squared term, since C4 is equal to negative 1, then that I should force C3 to be equal to positive 1. So with C1 equals C2 equals positive 1, C3 equals positive 1, and C4 equals negative 1, we've found a non-trivial way to combine these functions and cancel them all out and get 0. So that's proof that this collection of functions is linearly dependent. Linear dependence is usually a sign that one or a couple of your functions is kind of redundant. For example, do you really need sine squared when sine squared is the same thing as 1 minus cos squared? Linear dependence is a sign that one of the functions in your collection is redundant and is in some sense covered or addressed by the other functions in the collection. Now when the functions get more complicated, or when you get more than 4 of them, it becomes a lot harder to determine linearly dependent versus linearly independent by this sort of ad hoc guessing and checking method that we did in the previous example. A way more reliable way to determine linear independence versus linear independence is to use the determinant of a matrix. The determinant that we need is called the Wronskian. Yes, what a wonderful word. A student once told me that it sounded like an alien species who's come to conquer our oceans. So the Wronskian is a determinant of an n by n matrix. If you have n functions, then your matrix is going to have n columns and n rows. So if you have 4 functions, your matrix will have 4 columns and 4 rows. The first row is going to be filled up with the original functions, f1 through fn. The second row is going to be filled up with their first derivatives for f1 through fn. The third row will contain the second derivatives, the fourth row will contain the third derivatives, and so on and so forth, until the final row contains the n minus first derivatives. The beauty of this matrix is it gives us a totally clean and concise and concrete and reliable way to determine if a collection of functions is linearly independent or linearly dependent, without having to go through this nonsense that we went through in the previous example of using all kinds of trig identities and guessing non-zero values for these constants that would make the combination of these functions equal to 0. The Wronskian allows us to skip this entire thing that we just did. When you're using the Wronskian to determine if a collection of functions is linearly independent and linearly dependent, the collection is linearly independent if the Wronskian is non-zero and the collection is dependent. All you have to do is calculate the Wronskian and show that it is 0. Super similar to linear algebra if you've taken it. In linear algebra, if you wanted to determine if a collection of vectors was linearly independent, you threw them all into a matrix, calculated the matrix determinant, and if the determinant was non-zero, then the vectors were independent. And it's basically the same thing here, except that the matrix that we are calculating is the Wronskian, which is filled up with all these different derivatives of the functions. So let's go ahead and use the Wronskian to show that the functions root x plus 5, square root x plus 5x, x minus 1 are linearly dependent. Now it's completely possible to answer this question using the technique that we did in the previous exercise of trying to set up a combination of those 3 functions which is equal to 0, and basically setting up some educated guesses of the constants that would be necessary to make that kind of thing happen. And that would definitely be faster than what we are about to do, but it's also a little bit more artistic, a little bit more intuitive, and a little bit less algorithmic and reliable. So the Wronskian method that I'm about to show you is going to take a bit of time, but the upshot is that it's completely reliable and doesn't really require any guesswork. So I'm going to set up a 3 by 3 matrix, and then I'm going to calculate its determinant. 3 by 3 because we have a collection containing 3 functions. Those functions are going to form the top row of our matrix. The first derivatives of these functions are going to form the second row of this matrix, and the second derivatives are going to form the third row. Now I'm going to proceed with the following calculation as if you already know how to calculate the determinant of a 3 by 3 matrix. If you don't remember how to calculate the determinant of a 3 by 3 matrix, I'm going to put a link in the description to my Calc 3 video which covers that topic. So I'm going to take the entry in the top row, first column, and multiply it by the determinant of the 2 by 2 matrix, which excludes the first row and first column, which looks like it's going to be equal to positive 1/4 x to the negative 3 over 2. And just for future work, I'm going to write everything in exponential form because I think it's going to make it a little easier to simplify. Then I'm going to take the negative of the second entry in the first row, and I'm going to multiply that by the 2 by 2 determinant of the matrix which excludes the first row and the second column. So that also looks like 1/4 x to the negative 3 over 2. And then I'm going to take the entry in the third column, first row, x minus 1, and I'm going to multiply that by the determinant in the bottom left corner, which looks like it's going to be equal to positive 1/8 x to the minus 2, minus 1/8 rather, from 1/2 times negative 1/4. And then we're going to subtract what we get from the anti-diagonal product, which is negative 1/8 x to the minus 2, and then negative 5 over 4 x to the negative 3 over 2. Now I'm just going to go ahead and quickly clean up this expression in the bottom left by distributing through this minus sign. So not minus 1/8, but plus 1/8, and plus 5 over 4. So that reveals immediately that I can take this negative 1/8 x to the minus 2 and this positive 1/8 x to the minus 2, and those are like terms that can be cancelled out. So now let's algebraically simplify the rest of this expression to see whether or not the result is equal to 0. Okay, so doing the first distribution, it looks like we get 1/4 x to the minus 1 plus 5/4 x to the negative 3 over 2. Then for the second distribution, it looks like we get negative 1/4 x to the minus 1 minus 5/4 x to the negative 1/2. And then in the final distribution, it looks like we get positive 5 over 4 x to the negative 1/2 and negative 5 over 4 x to the negative 3/2. Isn't this wonderful? Look at this. We got positive 1/4 x to the negative 1, which cancels with the negative 1/4. We've got positive 5/4 minus 3 over 2 for the exponent, which cancels the final term in the back. And then we have these two terms in the middle, which are opposites and which also cancel. So the result of the Wronskian is 0, and therefore the functions are linearly dependent. There's a redundancy in there. One of them is being covered by the other two. Now, why is linear independence something that we care about? Well, suppose that you have exactly n linearly independent solutions to a homogeneous ODE of order n. So you have n solutions, none of them are redundant. All of them are somehow meaningful individually. Then all solutions to the ODE have the form number times f1 plus number times f2 blah 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 number times fn. So what's the huge takeaway? If you've got a homogeneous ODE and you want to solve the ODE, if you want to find all solutions to the ODE, all you have to do is cook up n linearly independent solutions. So in particular, if you're working with a homogeneous ODE of order 2, a second order homogeneous ODE, you can find all solutions by finding just two solutions. If you can find two solutions, neither of which is redundant, two independent solutions, then combinations of those two form all possible solutions to the ODE. Isn't that amazing? You can find an infinite collection of solutions just by finding two solutions and combining them. Wow. For example, suppose that we have the ODE y double prime minus 16y equals 0, homogeneous second order. Let's show that f1 and f2, which is equal to e to the 4x and e to the minus 4x respectively, let's show that these are two linearly independent solutions to the ODE. So if I take f1 and take its second derivative, then it's 16 times what I had originally. Same thing is true for f2. Its second derivative is 16 times what it was originally. And therefore both of them are solutions to the given ODE. So now let's check if they're linearly independent. Let's figure out whether the Wronskian is 0 or not. So two solutions, 2 by 2 matrix. The determinant is equal to negative 4 e to the 0 minus 4 e to the 0. That's negative 8, which is non-zero. And that means that these solutions are linearly independent. It's a lot easier with two solutions than with three, isn't it? So for my second order differential equation, now that I have two linearly independent solutions, I can describe all solutions. All solutions must have the form y is equal to some number times the first solution plus some number times the second solution. Absolutely every single possible solution to this ODE must have this kind of format, where C1 and C2 are real numbers. Incredible. So that's what we'll be doing over the next several days. We'll be trying to figure out different ways to cook up a couple of linearly independent solutions to an ODE, so that we can combine those solutions to describe every single possible solution to the ODE. That concludes today's material. We introduced the idea of a homogeneous differential equation. We talked about how homogeneous ODEs have a special property, that if you combine individual solutions, then you can get new solutions. We talked about linear independence of functions, and two ways to check for linear independence. And then we talked about how linearly independent solutions can be used to describe the complete collection of solutions to a homogeneous ODE.